Salina, so he is a relatively local person, unlike a lot of us. Right. And he is an alum of this department, but went on to graduate school where he got his PhD at the University of California, Santa Cruz. He is an astrophysicist, and he's worked on planetary nebula and a lot of stuff, but I think what we're going to do today is hear about some of his accomplishments as an astronaut. He was on 5 Space Shuttle missions, including one that he was the payload specialist that launched the Hubble Space Telescope, and also I think you were on the mission that repaired the Hubble Space Telescope. And this is the 25th anniversary as of April 24th of the launch of the Hubble Space Telescope, which has been a wonderful tool for the astronomers. So we're looking forward to celebrating that anniversary, Steve.
Thanks. For the last colloquium of the semester, I thought maybe it'd be fun to share some of what we did over the last 25 years, and actually even longer. Last week, I had a chance to go to the Institute and rub elbows with some of the guys I hadn't seen in a long time, and we were in the mode of, well, this is how I remember it. How do you remember it? Because we're all old and we don't remember stuff so well anymore. But my plan for today is to tell you a little bit about specifically the challenges that HST represented even before it was launched and then while it was on orbit. I will share the conclusion that Hubble has been a remarkable instrument, and as far as we can tell, there's nothing today that appears to be limiting in the subsystems. Everything seems to be working fine. One of the rate gyros is a little flaky. The new solar arrays are a little bit degraded in their performance, but there's no reason to expect it can't continue for another 5 years or longer. Here's some context. This is actually the orbiter Discovery when it was rolling out to the launch pad for its final flight. Discovery is the orbiter that launched Hubble. One of my favorite astronauts and was my boss for a long time, John Young. He had a lot of colorful sayings. This was one of them. There were roughly 30 of us that accepted whatever risk there was to be involved in the Hubble missions. And I think every one of us would say it was worth it. You can probably read that. It says anyone who sits on top of the largest hydrogen-oxygen fueled system in the world, knowing they're going to light the bottom and doesn't get a little worried, does not fully understand the situation. John was also asked before STS-1, if you remember in the mid-70s, we did this thing called Apollo-Soyuz. It was part of a daytime program between the US and Russia. So it was still relatively fresh in the minds of the press. And the press asked John, well, do you think another mission between the United States and Russia would be appropriate? And John said, yeah, he thought we should fly STS-1 with a Russian crew. So, but this talk is about telescopes, and in particular telescopes in space. And it's interesting to think back to how far we have come in the last 100 years or so. And by the middle of the 20th century, Shapley had shown that the sun was not at the center of the Milky Way. It was actually out in the boondocks. Hubble had found Cepheids in Andromeda and was able to show that these fuzzy spiral nebulae were really other galaxies. He also had determined that the universe was expanding by putting together the already known observation that most galaxies are redshifted with distance indications from Cepheids. And the age of the universe could be estimated. Now when Hubble did it, it was sort of a gutsy call, because his value of the Hubble constant led to an age of the universe that didn't make any sense. But he still gets credit for it, and we'll come back to this point. At the time we launched Hubble, we didn't know the age of the universe to about a factor of 2. And one of the important projects for Hubble was to resolve the issue of how old is the universe. But even back in the mid-20th century, scientists were thinking about the prospects of telescopes in space, and the leading proponent was this guy, Professor Lyman Spitzer, who spent a lot of his career at Princeton and wrote a 1946 paper, you see the title there, talking about the advantages of a big telescope in space. NASA began planning for the LST in 1968. You probably might think LST stood for the Lyman-Spitzer Telescope. It actually stood for the Large Space Telescope, because you're not allowed to name stuff after people while they're still alive. And Spitzer was still alive. In fact, he came to the launch in 1990. NASA began a Phase A study in '73. At the time, HST was a 3-meter telescope, but budgets being what they are, it ended up being a 2.4 meter, and it was officially a new start in 1977. So people have been working on Hubble really since the late 60s. It was named for Edwin Hubble in the mid-80s, and as Tom mentioned, we celebrated the anniversary a couple weeks ago. Hubble was part of this thing called the Great Observatories Program. Charlie Pellerin was at NASA headquarters at the time, head of the science division, and I think it was really clever. I don't remember all of the details, but rather than have the different astronomical communities fighting amongst themselves for budget priority, he proposed this idea of let's build a series of great observatories that span the electromagnetic spectrum. We'll launch them all into space, and it'll be wonderful for astrophysics. And Hubble was the first. This alphabet soup is the listing of the original science instruments in Hubble: the Goddard High Resolution Spectrograph, the Faint Object Camera, Faint Object Spectrograph, High Speed Photometer, the Wide Field Planetary Camera, and the FGS, which is the Fine Guidance Sensor, which is how the telescope points with stability, but you can also use it for astrometry, so it counted as one of the science instruments. And there were 3 key projects established in 1983 that were going to use a lot of Hubble time because they were important projects. One of them was to to determine the Hubble constant with an accuracy of 10%. The second was to observe the Lyman alpha forest in the direction of, I think, 100 different quasars. And the third was to take a medium deep image of nothing in particular as a gesture to the unknown. So those were the 3 key projects. HST was unique because it was the one great observatory that was actually designed to be maintained while it was in space. It's clear, we know we are really good at building spacecraft that last. If you've had any of my classes, you know I always ask, how long were the Mars rovers supposed to last? The answer is 90 days, and that was over 10 years ago, at least for Opportunity. Spirit is sort of dead, but Opportunity still works. The initial plan was to bring HST back every 5 years and then fix it on the ground and relaunch it. And I was talking to Bob Odell last week. Bob was the HST project scientist at the time HST was approved as a new start. And Dave LaCrone, who's been involved in HST since '72, and he was the project scientist about the time of the second servicing mission for the duration of the program. And the question was, who made that decision? And the answer was, none of us can remember. We think it probably wasn't any particular person, but rather it seemed collectively the decision to leave it on orbit made more sense because it was less risk to the telescope and less expensive. It was designed to last 15 years. And servicing has been critical to HST's success. I should say that AXAF, which became Chandra, which was one of the great observatories, was originally designed to be serviced. And in 1992, the program budget was cut. And one of the things they did to get back in the budget box was delete servicing. If you delete servicing, then you don't have to budget for new instruments, you don't have to budget for standing army of contractors, you don't have to budget for additional launches. And so, as a result, it also didn't need to be in low Earth orbit if you don't need to get to it. So Chandra actually goes about a third of the way to the moon. Because of the need to service it on orbit, one of the things that was done was to sort of partition all of the components into those that you would change out or fix on orbit and those you wouldn't. And so many of them were designed to be serviced or replaced on orbit. What that means is if you've got a handle, it's a really big handle. If you've got a fastener, it's a really big fastener. If you've got screws, they're captive, so they won't come out. Imagine trying to hook up my little laptop, wearing oven mitts. That's what it would be like if you were trying to service something in orbit that wasn't designed. As it turns out, we ended up servicing lots of things that weren't designed to be. And part of the reason for Hubble actually was because in the 60s and 70s, we really felt we had come as far as we could come in the development of large ground-based observatories. We did not foresee the need or the ability to develop large mirrors that were not monolithic any longer, but rather made out of segments, and that you could control those segments with computers, and you could do adaptive optics, and all of the things that makes it possible today to build 30-meter telescopes. But the combination of the orbiting facilities and these new ground-based facilities has been an incredible advance for astronomy. 3 of the great observatories are still flying. GRO is the one that was deorbited on purpose in 2000 because it had gyro failures, and they were worried that they had one more gyro failure, then it could come down without our ability to control where. I thought, hey, you know, let's take our chances, but NASA wasn't going to do that. So this is Hubble in the test facility in Sunnyvale before we launched it, of course. It's not a really good picture, but those are some people, so you get a sense for the scale. And this is what we were telling people that Hubble would be able to do back in 1985. So you can look at that and you can make a judgment about, you know, how we did. There are a lot of things that needed to be done before you could put Hubble in space, and in fact, before you could even get a new start, because one of the things you had to do was sell the idea to Congress. At the time, there was a school of thought that said, you know, rather than spend a bunch of money, like $2 billion, on a space telescope, why don't we build a bunch of 200-inch telescopes and place them around the world? Wouldn't that be a better way to spend your money? 3 of the principals, Dr. Spitzer, John Bacall, and Jesse Greenstein, were strong advocates for telescope in space. I found out from Bob Odell, I didn't know this, that Jesse Greenstein actually was involved in a rocket launch. One of his instruments, I don't know what it was, in the 40s. And when they launched it, the aperture didn't open, and he got no data. And Bob told me that Greenstein was sort of turned off to space astronomy at that point. But he did turn around and become an advocate for building HST. One of the things that we needed and didn't have was a good guide star catalog. The fine guidance sensors on Hubble are so good that we found out we didn't have enough stars that were faint enough that had good positions. And so Barry Lasker, who Bruce and Barbara would probably remember Barry. Barry was at CTIO when I was there as a postdoc. Took the lead in developing a good guide star catalog that had faint stars with accurate positions. The scheduling software was a real problem and was slow to develop. We realized, of course, that we had the telescope on the ground for the last time, and so we were very interested in developing all of the tools and the techniques we're going to need for the next 15 years to surface HST on orbit, because we weren't going to get another chance to do fit checks. And that was of particular importance because in 1984, we took advantage of the fact that this satellite called Solar Max had failed in orbit to demonstrate that we could go repair it with astronauts from the shuttle. It was not designed to be repaired, but we developed a plan and knew what to do, and we were going to capture it with a friend of mine flying over in the manned maneuvering unit with a little device that would capture a trunnion pin on the satellite, and then they'd fly the satellite back to the shuttle. Well, when he got over to the satellite, the trunnion pin wouldn't capture. They ended up capturing it with a different method, and the repair was successful. And what we found out after the fact was some engineer down in Florida, right before launch, had decided, wouldn't it be better to add a little insulation around this particular location on the satellite? And it was never documented. Nobody knew it was there, I guess, except him. And so this device we built didn't fit. And so we were really worried about making sure we understood every interface that we were going to deal with on HST. Because we're going to leave it on orbit and go back to it over time with shuttles, we needed to figure out how high do we have to get it before it's worth leaving it there. If you don't get it high enough, then it's going to come down, and you're going to have to launch more and more missions just to keep it at the right altitude. And I'll show you a chart in a second. On our deployment mission, we needed also a quick response capability because the solar arrays were stowed for launch. They got deployed after the telescope was removed from the shuttle cargo bay, and if the solar rays didn't come out, then the telescope would die unless we were able to get outside and do something about it right away. We also weren't allowed to open the aperture door. I argued against that and lost. So that meant that once we released it, if the aperture door didn't open, we'd have to go back to it and capture it and do a manual intervention. We had a bunch of robotic arm procedures. Again, HST doesn't have its own propulsion system, so the shuttle raises the orbit periodically. Mirror polishing was behind schedule. The optical telescope assembly was behind schedule. That kept slipping the launch date. And then the Challenger accident happened. I was actually assigned to the mission in 1985. And then when Challenger happened, obviously that was a bad thing for the space program, but it did enable a lot of these other things to get done in time. And then eventually we launched in 1990. This is, I pulled this out of some of my old files. This is a chart of apogee versus perigee. And at the time, we were flying shuttles to about 150 nautical mile orbits. That's somewhere over here on this graph. This is the nominal deployment altitude, which is about 320 nautical. The chart was meant to suggest that if we didn't make it, then there were going to be some decision points where management would have to step in and decide whether we could leave it or whether we'd have to bring it back. So if we got up to, I don't know what this is, about around 300 miles, then it might add one additional servicing mission to the lifetime of the telescope just because of the lower than targeted orbit. If we didn't make it to at least 270, it probably wasn't going to be worth leaving it. So this was kind of challenging. I used to tell people we took it as high as you could go in the shuttle. I said that the other week in Baltimore too. It turns out that's not really true. It's as high as you can go in the shuttle and still get home. I got involved sort of by accident directly with Hubble in 1983. One of the things we learned early in the shuttle program was the shuttle glows. It's due to atomic oxygen interacting with the material, particularly the material in the shuttle's thermal blankets. And this is a picture of what it looks like. And so the HST guys were really concerned that, you know, if they get glow, that's going to be a real issue. And so on my first mission, I took along a camera and a spectrograph. That's the slit, and we took some spectra to characterize the glow. And what we learned was that a lot of the materials used, particularly in the solar rays, were not tolerant of the atomic oxygen. The glow, in fact, wasn't going to be the big problem. The big problem was that they would just degrade on orbit. Here's a quote that I stole from an ESA guy when they discovered this problem. So they ended up having to redesign the solar rays with new materials that were oxygen resistant. Again, because of the Challenger accident, they had time to get that implemented. And on the plus side, as I said, we were able to put more efficient solar cells. The original solar cells were about 12% efficient. So it all finally came together in April of 1990. This is Discovery with HST. This is Columbia. Ironically, the first mission with Hubble had another shuttle on the pad, and the last mission to Hubble had a shuttle on the pad. And I'll tell you why when we get there. This was a coincidence. The other was on purpose. This was the Astro 1 mission that was sitting there waiting to launch, and it ended up sitting there for about 6 months because there was a leak in the propulsion system that they were trying to troubleshoot. This is HST on orbit in the payload bay. It's deployed by the Canadarm, the robotic arm, and that was a challenge, which I don't really have time to go into, the way the arm performed with a real massive payload on the end. But it was really challenging and somewhat terrifying. But we did manage to get it out of the payload bay and got the first solar array deployed. And then we were given they told us they were going to deploy the one you can't see. It's on the far side. And we were able to watch it on a TV camera located on the aft end of the shuttle. And what happened was the canister opened and the array went out, and it went like that and stopped. It was just the stored energy in the system. And so that's not good, because Hubble is not power positive. It's running on batteries. We had 6 hours of battery life on that day, and we'd used probably 2 or 3 by now, getting it to this point. And so we ended up beginning to execute this quick response EVA that we had developed. They eventually discovered that what the problem had to do with was a tension monitoring sensor that was designed to shut the motors off if it detected some asymmetry in the deployment. The solar arrays are pretty delicate, and it was detecting a problem that didn't exist. So eventually they bypassed it and got the arrays out, and that worked. And we actually then were able to complete the deployment. There's an interesting story about why that's the only picture ever taken of the release of Hubble, but I don't have time to tell you that story either. So we landed all excited that we had successfully deployed HST, and I remember wandering around the hill with a whole fistful of first light photos like this, telling all the members and their staff that, yeah, it's supposed to look like this. We just haven't focused it yet. This shows the better resolution that Hubble provides, but it also showed a real problem. As you guys no doubt remember, we had spherical aberration in the mirror. And people figured that out pretty quickly. And that meant, of course, there was nothing you could do about the focus. There was no way to focus it precisely. The point spread function turned out to be about 10 times worse than the design. And if you're willing to throw away light, you could still get pretty good results, because you could just take the inner part of the point spread function and it would give you pretty good resolution, although you're limited to bright objects. Spectroscopy wasn't too much affected, but photometry was dramatically affected, and bright objects were not possible. And this is actually an image taken of NGC 4261, which is a big elliptical galaxy that's a radio source. It's an AGN. And this was done with the aberrated mirror. So we were still able to do science, but nobody cared. All they cared about was the fact that we had a mirror that had cost all this money that had spherical aberration. And these were dark times. I saw Mikulski last week, and she still talks about techno-Turkey, although now she basks in the glory of her efforts to help save the telescope. This is Letterman's top 10 from May 15th, 1990. There's obviously the Newsweek. We were big news, not in a good way. This is Warren Leary's article in the Times, and NASA commissioned an investigation into what happened, led by Lou Allen, who was the director of JPL at the time. And pretty quickly they figured out what happened. The mirror was made by Perkin-Elmer. Well, actually, the glass was made by Corning. It was ground by Perkin-Elmer. And it was the most precise mirror ever created. The surface was perfect to within 10 nanometers. The problem was it wasn't the right shape. And they removed too much glass from the edge, about 2.2 microns too much. And the reason, which again, I'd love to go into detail, don't really have time, was there's a device called a null corrector. A null corrector is a device you make to verify the surface of a complex mirror. Basically, it makes it look spherical. So you can use the standard interferometric techniques that opticians have been using for a long time. And so the bottom line was they made it improperly. There was a spacing error of 1.3 millimeters in the null corrector, and so they ground it, therefore, to the wrong shape. It's actually worse than that, because there were 2 null correctors, and one of them was right and one of them was wrong. and they had both sets of data, and they chose to believe that the one that gave the wrong, said that the mirror had an aberration, they chose to believe that was wrong. And they chose to believe that the one that said the mirror was okay was correct. So I visited the backup mirror a couple weeks ago. Corning made two mirrors that were identical. One went to Perkin-Elmer and one went to Kodak. They were both in competition for the contract to build the actual mirror for Hubble, and Perkin-Elmer won. Kodak went ahead and ground the mirror anyway. It's not illuminized, so you can see kind of what it looks like. And it is right. They, in fact, even went so far as to prove that this mirror was ground properly. So there was discussion at the time, hey, we've got a good mirror we know is good. Maybe we could build a Hubble 2 real quick and launch it. Well, clearly that was going to take some time. It was going to be expensive. So some clever guys came up with another idea called the COSTAR. Stands for Corrective Optics Space Telescope Axial Replacement. I don't know who the heck came up with that acronym. But this is the actual sort of engineering model that they probably, it's the sort of thing you would take to headquarters and put on a manager's table and show him how this thing's going to work. This, you can't really tell. This is a depiction of the focal plane of HST, and each of the science instruments has one or more apertures in the focal plane. This is the faint object camera apertures. This is the faint object spectrograph apertures. These are the Goddard high resolution spectrograph apertures. And so the idea was you could build this thing that had deployable arms with optics ground specifically for each of the apertures for each of the instruments, and you would insert it in the beam from the OTA. And it would correct the aberration and all would be well. I thought that was the biggest bunch of crap I'd ever heard. Michael?
So looking at that drawing, is most of the light wasted? Because you have these big circles and you have these little
Wasted.
I mean, so
There are places in the field of view where there is no aperture. I don't know if I would say that's wasted.
But the field of view is significantly smaller than the focal plane, right? So the
Right.
field of view, so the actual light falls into a very small.
And these are the fine guidance sensors as well.
I'm sorry, I'm just looking at that circle and you showed me different
Yeah.
areas inside the nice. Well, there's a lot of empty space there. So.
I guess that's true.
There's no light falling on the empty part, right? It's not like light just.
Yeah, there is light falling on the empty
little
part.
bit, right? But
Yeah, a little bit.
Yeah.
Because that's the secret to COSTAR, as I'll show you in a second. This is actual photograph of the optics on COSTAR. And this is how it works for the faint object camera specifically. So in the original design, the light from this part of the telescope would come to the aperture, in this case for the F96 camera. So what COSTAR would do would be extend an arm into the field of view and it'd have a couple mirrors. One mirror would be on the underside of a mask. And so the original light beam would hit this mask and go no further. And a different part of the field of view would hit this mirror and be reflected into the aperture of the camera. So you're actually getting light from a slightly different aberrated point in the field of view. It's actually, the mirrors had to do a couple of things. One of the things they had to do was to correct for the aberration. That was, at least in principle, easy to do because we knew what the true figure of the mirror was from the investigation. In this case, the mirrors also had to correct for the astigmatism. HST is a Ritchie-Chrétien design, which is a version of Cassegrain, but the mirrors are hyperbolic, and one of the consequences of using hyperbolic mirrors is you get good field of view imagery, but one of the things you are left with is astigmatism. In a parabolic mirror, you get coma. And in HST, because we wanted to use images for astrometry, we didn't want coma because coma is asymmetrical.
What is coma?
It's an aberration that is a property of parabolic mirrors that at the edge of the field of view produces an image that looks more like a teardrop than a real star. In big optics, a lot of it is about trading different aberrations for different aberrations. In this case, astigmatism was preferred, but the astigmatism here is different from the astigmatism here, and so the mirrors also have to introduce astigmatism so that the F96 camera will take it out. And this is a drawing of how it would work. Same basic thing that I just told you. Light comes in from the original light path and is blocked, and then light from a new path is reflected back to this mirror and then down in the aperture of the camera. And I thought that had no chance of working. But it did. So one of the primary goals of the first servicing mission was to take CoStar up and install it. To make it work, we had to put it in the axial bay, so something had to be sacrificed, and the high-speed photometer was chosen. We also installed the second generation WIFPIC, which had its own set of correcting optics, so CoStar didn't affect WIFPIC. One of the things we noticed after the deploy mission was the solar rays introduced a jitter into the pointing system just because of the thermal effects of going from daylight into night and night into day. Turned out that was a big damn deal. And we devoted a lot of HST's computing power to trying to keep the telescope pointed correctly. So it turns out that actually the #1 priority, despite the aberration, was to replace the solar rays with ones that weren't going to introduce jitter. We were under a lot of scrutiny, and this was billed as the most important NASA mission since Apollo 11. This is the guys on orbit, and this is the replacement of the original wide field camera. There's a hole there now. And the way we did these things is when you took the old instrument out and put it on a fixture for temp stowage, then you get the new one out, put it in, and then take the old one and put it in the enclosure. And I forget what we called this thing. That's where you would hang the science instruments while you're in the process of changing them out. To replace the solar rays, the crew went to roll them up, and one of them didn't roll up. And so they had actually practiced right before launch how you would get rid of it if that actually happened to you, because they were worried that it might. And so Kathy Thornton is standing on the end of the arm holding this thing, and then she let it go, and the shuttle backed away, and a thruster hit it, and it flapped like a big bird. It was really interesting. But the mission was successful. The focus was restored, the jitter was gone, WIFPIC 2 is in there with new gyros, and we got a lot of confidence that we could actually do this stuff, which was pretty important. However, in the new arrays they put in there, even though there wasn't a jitter, there was a persistent static twist, which turned out to be a real big deal for us on the next flight. But here's some images showing how well CoStar worked, and so I was wrong about that. It actually worked great. And in fact, in WIFPIC 2, if I remember right, I think the new detectors compensated for the light loss from the additional optics to the point where the throughput was actually better than the original spec. Greg may remember that better than I do, but that's what I recall. So now we were able to do some of the key projects. This is the original Hubble Deep Field, which was the gesture to the unknown. This was taken over, this was a 10-day exposure taken in late 1995 of a little region of the sky below the handle of the Big Dipper. Almost everything you see in there is a galaxy. It was intentionally selected as a place where there was away from the plane of the galaxy and away from known clusters, so we didn't really know what we would see, and what we saw was more galaxies than most of us expected. And also, the Hubble Key Project to determine the Hubble constant was able to be accomplished. Because when we had the aberrated mirror, we could get, this wasn't generally known, but we could get the spec resolution or the spec sensitivity, but not both at the same time. And you needed both at the same time to be able to do this project. And so that was done in the mid-90s. And so we got to go back in '97, and there was a lot of discussion at the time. You know, we kind of dodged a bullet. We had a bad mirror. We managed to get it fixed. Maybe we shouldn't screw with it anymore. But the whole premise was that we can keep new instrumentation in Hubble for 15 years or longer, keep it a state-of-the-art observatory. So in the end, they decided we would go ahead and install STIS and NICMOS in place of the GHRS and the faint object spectrograph. The big deal for us was all this stuff having to do with the integrity of the solar rays. They were really worried that if we put loads on them, that they would just buckle and we could lose the telescope. So a lot of planning went into how to deal with all of that, which again I don't have time to talk about. But in the end, we were successful. That's the launch in February of '97. That's capturing HST and putting it in the berthing fixture here in the aft. And then we can go work on it. You might be able to see some of the static twist and the solar rays in this image. You might be able to tell if you're sitting up close. There's a little white dot right there. That's a hole. There's the high gain antenna took a hit. There's a 1/4-inch hole in the antenna. I'll show you if I have time later that HST takes lots of hits. The interesting thing is we've never really seen any consequences of it. So we were changing out the instruments. This is Steve Smith with either the STIS or NICMOS. Fine guidance sensors being changed out here. They also had their own correcting optics installed. On the second day, when we had Hubble, we got to see the side that faces the sun preferentially. And what we saw was bad news for the insulation. It was distressed, it was peeled up, it was discolored, and there's a lot of concern about both the thermal properties being compromised and whether this stuff would flake off and become a contamination source. And so they wanted us to build some patches that we could install over the worst parts that we had discovered. And so this is Scott Horowitz, who built some patches out of material that we had on board. I remember clearly that they sent him a procedure on how to do this. And it was 30 pages long. And it really pissed him off. He said, I don't want a procedure. So they sent him 35-page procedure. And he said, send me a damn picture. I don't need a procedure. He said, send me a picture of what you want it to look like. So finally they sent him a drawing of what they wanted it to look like, and he built it. And then they extended our mission and gave us another EVA, and we went out and put the patches on the telescope. And it's not commonly known, but we all signed it with a black Sharpie. I don't know what that does to the thermal properties of the insulating blanket. They were removed on the last servicing mission when the ground developed a far more robust and more proper repair technique. And Grunsfeld took it off, because I remember asking him a year or so later, I said, what did you do with it? Because I'd sort of like to have it back. He said he lost it. He meant overboard. I mean, it went off into space, so I guess I'll never see it again. But although this was not the first detection, this was an early release scientific result from STIS. This is M84, which is an elliptical galaxy that was suspected harboring a black hole, and this is the Doppler shifted gas around the center, and it's going at about 400 kilometers a second. If you do the math, it's 300 million solar mass black holes. So HST was able to confirm the existence of black holes. Rate gyros were always a problem. There was a generic deficiency in the build of the rate gyros, and they had replaced a bunch on the first servicing mission, and then they were all working when we were there, and when we left, 3 failed. Now at the time, you needed 3 of 6 in order to be able to do science. They were working on a 2-gyro mode, which I think they actually did manage to somehow certify before the third servicing mission was launched. But that sent us into sort of to general quarters, needing to put a mission together quickly to go back and replace the gyros with new gyros. So there had been a servicing mission 3, and it ended up getting divided into 2 parts. And they called it 3A and 3B. So when you hear the last servicing mission was servicing mission 4, it was actually servicing mission 5. Before we could launch it, a 4th gyro failed, so HST went into safe mode. So it wasn't doing science for a couple months. The mission launched on December 19th. It was actually delayed somewhat because when we launched Chandra on STS-93, we had a short right at launch. And actually, for only the 2nd time in program history, we ended up shutting down before the target main engine cutoff targets. And they stood down the fleet to do inspections of other wiring runs and other vehicles. So, and then, if you're old enough, you remember Y2K. We had a 4th EVA that we decided to cancel so we could get the vehicle back on the ground before December 31st, 1999. But when they got there, what the guys saw, you might not be able to see it, there's this little wire sticking out. It's called a hinge wire, and it holds the solar cells in the solar array. And there were 2 problems. One was this could very likely be an EVA hazard. Second problem was, depending on why it's doing that, you could have structural issues with the solar array. So the ground guys worked really hard to see if they could determine whether it was safe to proceed. Ultimately did decide it was safe to proceed. One of the leading ideas actually was that this had been produced by a hit from a piece of micrometeorite or orbital debris. Another idea was that it's thermal stressing just from the day-night cycles all the time. If that's true, then you've got a potential structural issue. When we got the solar array back on the ground, it turns out that the debris hit was the correct explanation. So the guys were able to do the EVA. One of the things they were going to do was change out the computer. I don't actually remember for sure, but I don't think the computer was ever designed to be replaced. The DF-224 is a pretty well-utilized, space-qualified computer. It's not very capable. As you can see from the description, it's got 8K 24-bit words, 32K of memory, and that was what was running HST. When they put the new computer in, it was an Intel i486, 25 megahertz, and you can't probably see the cables in the way, but it improved our computing power by about 20. Doesn't sound like a lot, but it was enough to put some of the computing algorithms on board the spacecraft, which made for more efficient science operations. And we replaced all the gyros. The second part of Mission 3 was to install ACS. When we launched NICMOS, my recollection is that we knew we had a heat problem when we launched it. And we knew it wasn't going to last 5 years. We thought it might last 2 or 2.5, and I think it did last 2. So the guys at Goddard figured out how to develop a cryocooler, which would be installed on NICMOS to cool the instrument. The ACS went in place of the faint object camera, and we finally got rid of the old solar arrays with new rigid solar arrays, which were actually built for the Iridium satellite constellation. Because they were more powerful, we installed a new power control unit, which involved completely powering HST off, which is something nobody had ever anticipated doing. That was sort of a gutsy call. But it worked, and the new power available from the new solar arrays allowed us to use more than one instrument at a time for observing. I don't have time to talk about what this means, but we almost couldn't do the mission because we had an issue with the orbiter that we were actually in the end able to work around. So this is what the new solar arrays look like. They're sort of like card tables. They just fold up and they're rigid. They're smaller in area, so they don't introduce quite as much drag on HST, which is good. And they were a lot more power than we needed. This is the installation of the ACS. This is actually the faint object camera coming out. And when we got the solar arrays home, we looked at them to see, kind of what they'd been exposed to. And this is just one little part of the solar array, but you can see they pretty much got peppered with micrometeoroids or orbital debris. One of the things they always had us do was go survey the solar rays every time we would show up, and I remember you just see holes all over the place. Usually not big holes, but holes like that.
Steve, those holes would have pierced the spacesuit, right?
Say again?
Those holes would have been, those meteorites would have been sufficient to pierce the spacesuit?
I doubt it.
Okay.
Yeah, the spacesuit's pretty well developed with multiple layers and multiple layers are pretty effective against this kind of stuff. So, after the second part of the third servicing mission, we had the Columbia accident. And Sean O'Keefe was the administrator at the time, and he canceled all of the remaining HST servicing missions. And the only missions we could fly were ones that would go to the space station. So if the shuttle were damaged, you could go to the space station and you could hang out there until the rescue shuttle could come get you. And HST, of course, isn't in an orbit that would, despite what they tell you in gravity, HST is not in an orbit where you can then go to the space station. Also, because of the cause of the Columbia accident, debris strikes, including micrometeoroid and orbital debris, became a real program focus. And MMOD strikes are a lot more likely in HST's orbit than they are in the normal lower orbits that we would typically fly. We also spent a year trying to figure out, is there a way we could repair Hubble using robots? And this is a cartoon of how that was supposed to work. This was a robotic stage that would attach to the back end of HST on what we call the towel bars. This is a motor that would eventually be used for deorbiting or raising HST. This is a dexterous robot made by the Canadian Space Agency. Down here is a storage volume that has new instruments or spare parts. And the idea was you'd use this guy and go around and open all of the doors and pull out the old instruments and put in the new instruments. We played around with that in simulations for a year. It never really worked very well, partly because Hubble is designed for guys with hands. And so it was hard to make these end effectors work very well. Also, there's a time lag. So if you're the guy on the ground, this was not autonomous, it's been operated by some guy on the ground. And so if a 5 or 6 second time lag was a real problem in trying to do some of the delicate work. In the end, Mike Griffin replaced Sean O'Keefe, and he reversed the decision and allowed one more servicing mission to fly, which was STS-125. But we had to have a rescue orbiter on the pad in case something happened. And again, if I had time, I'd explain how that was going to work, because that's another thing I thought had no chance. But we did launch one more and put in 2 new instruments, Wide Field 3, Cosmic Origin Spectrograph. We upgraded the gyros and the batteries. We repaired STIS and ACS, both of which had suffered failures. And they put this new insulation repair on, which caused them to lose my autographed collectible. And they put a soft capture mechanism on the underside so that sometime in the future we could send a robot spacecraft and at least deorbit it if we need to. They brought CoStar home because it was no longer required, and they got some pretty neat footage for, I finally saw the 3D IMAX movie the other day for the first time. It's actually not too bad. So this is CoStar coming out. Of course...
Why was CoStar on this?
Say again?
Why didn't you need CoStar anymore?
Because all of the new instruments had their own corrective optics in them, so you didn't need the kind of artificial correcting optics. WIFPIC 2 was a real problem. It's got a locking bolt on it, and you have to undo the locking bolt in order to get it out. And the EVA tools all have torque limiters on them because you don't want to break a bolt. You want to make sure you impart only the torque that the bolt's designed to see, but that wasn't enough. Eventually, they decided to remove the torque limiter and see if they could get the bolt out, knowing that you might break the bolt, and if you did that, then WIFPIC 2 is going to be there forever. And when they did that, it actually worked, and they got the bolt out, and they got WIFPIC 2 replaced. This was a STIS repair, and STIS was not designed to be repaired, so it had a couple of hundred non-captive screws. And the way we handle a situation like that is you build a special plate that goes over the location of the screws, and then you remove the screws and they come out of the connector, but they come into this plate where they're captured. So the first thing you do is attach this capture plate, and then you take all the screws out and you don't lose them. The problem was, to get that capture plate on, Mass had to remove a handrail, and the screw at the bottom of the handrail was stripped. And so he couldn't get it off. And so he was able to get the top one off, so does anybody remember what they told him to do?
Tear it off.
Tear it off. They said just grab it and break it off. That was a pretty gutsy call. He did, it worked, and they got stitched repaired. And this is the soft capture feature, now affixed to the back end of HST. That's with pick 2. I took that picture last week at the Air and Space. It's actually a little bit worse than it really was, but all of these were debris hits. What the guys do is they go and they core each of the little hits. So they take out material around the hit itself because they want to characterize what the material was that caused the hit. In our models, to predict potential damage, we need to know what the debris is made of. And it seems to be made of all kinds of stuff. A really common source of debris is paint, turns out. There's also, we found evidence of the kind of plastic used in circuit boards in some of these impact sites. I remember, it didn't have anything to do with Hubble, but I remember on STS-7, there was a chip out of the window that was analyzed post-flight, and what they discovered was that it was borscht. That the mere cosmonauts had dumped their garbage overboard, and some of it had hit the shuttle. This is about 680 or so holes that, of various sizes that were in WFPIC. This is CoStar, after it came home, of course, and this is that faint object spectrograph that we took out in 1997. It's sitting at the Smithsonian also. Perhaps the thing that maybe Hubble may be the most famous for is the discovery of dark energy, for which Perlmutter and Adam Rees and Brian Schmidt won the Nobel Prize a couple of years ago. And everyone probably has his or her own list of, Hubble favorites, but this was in this month's Sky and Telescope, how Hst Changed Astronomy. We always advertised that we'd be able to get imagery of solar system objects that were comparable to what we got with the Voyager and Pioneer flybys. Bob Odell's contribution to seeing protostars and stellar nurseries in Orion, measuring the proper motion of M31 and the LMC, showing that LMC is probably not bound to the Milky Way, and that M31 and the Milky Way will collide and make probably a big elliptical someday. Galaxy morphology and supermassive black holes. The deep fields have been incredibly important. Greg is an expert on how they've been so useful for looking at galaxies. Hubble constant, dark matter, dark energy, and this thing called Hubble Heritage. Hubble Heritage was a program specifically designed to make Hubble imagery available to the masses. Sometimes they would take pictures that were obtained for scientific reasons and just release them because they were cool. Sometimes they would actually take images that were just cool and release them. One of the things that Hubble represents that probably no other program, including Apollo, was able to do was keep the public interested for decades. Not just the public, but Congress and the administration. When Hubble servicing was canceled by O'Keefe, it was really the public agitating their congressional representatives that got the program reinstated. There are 3 Saturn V's lying on their sides in Houston, Huntsville, and KSC because we lost interest in Apollo. But somehow Hubble has managed to maintain interest over decades. And I'll just conclude by saying I tried very hard to find somebody that would tell me, what's going to fail next on HST that we should worry about, and nobody has anything. The solar rays have lost some efficiency. We will get to the point where we can't run multiple instruments anymore because we don't have enough power. There's one gyro that's a little bit flaky. I think it's gyro 5. It may or may not have been declared failed, but the others are working. And officially, NASA says that it expects HST to work through 2020, which would give us, assuming we can really launch in late 2018, give us some overlap with JWST, which is pretty nice. Anyway, thank you for allowing me this trip down memory lane, and I'll be happy to answer questions. Yes, sir.
About the optics, manufacturing defect. Tell us. I'll first say what I heard at the time, which might have been completely false. So I was told that the defect was sufficiently bad that if anybody had just looked through the telescope, if you'd done a responsible job on a test bed, it would have been picked up before being launched. But there was such overwhelming confidence, and the military wouldn't let them use a high-quality test bed, that they never did the test.
They never did an end-to-end test. That's true.
Just all the way through.
They did have data that said the mirror was flawed.
No, but you do the end-to-end test. Why was no end-to-end test done?
Well, I can't answer that conclusively, but I would say a couple of things are likely. One is there was a legitimate technical argument that said they didn't need to in the context of the schedule and budget pressure they were under. I think if they had said, look, what we really need to do is we need to do an end-to-end test to make sure we know what we've got, it's quite likely that there would have been an opportunity to cancel the program. So they had, but they did have test data that said it was right, and they had test data that said it was wrong.
But is this I had heard that this was let's say, an institutional screw-up where engineers and competent people were frustrated by management. Or was this just an engineering mistake?
No, there was the added complication that there was great tension between PerkinElmer and NASA.
Why would anybody go a rat's ass for PerkinElmer?
They were doing
PerkinElmer.
They're doing the work.
They have to deliver.
Right.
NASA has the money.
Right. And they delivered. And we paid for it. And it was wrong.
So how did you feel about that? You're an insider and you do all this.
I felt, well, I wasn't there at the time. There were so many management lessons learned from that. NASA wasn't talking to PerkinElmer. PerkinElmer wasn't talking to NASA. There's evidence PerkinElmer was covering up issues they were having. NASA was not bore-sighted on getting to the bottom of that. You can probably blame a lot of different people. The bottom line is we had the data that said it was wrong. And whatever reason, institutionally, we chose to ignore it. Now, in the end, it all worked. If they had fessed up and the program had been canceled, then we wouldn't have HST. I'm not saying that that's the right thing to do. I'm just, isn't it interesting?
So mine's actually a little follow-up on that. Who actually did manufacture CoStar and design it?
Ball Aerospace?
Okay, so it wasn't PerkinElmer.
No, it was not PerkinElmer.
Yeah, so you put that docking mechanism on Hubble. Does that mean that like a Soyuz or something could service it if need be? Or,
Soyuz probably couldn't.
Okay.
But Elon Musk has recently been talking about how he thinks they can do it with a Dragon.
Cool.
I'm skeptical, but I've been wrong a lot about this stuff. Dragon doesn't have a EVA capability, so if you're going to do it with people, you got to figure out, if their avionics is really certified at vacuum and things like that. But they have put together presentations that say how they can do it, at least notionally.
Back there and then, go ahead.
Instrumentation aside, how stable is Hubble's orbit right now in the foreseeable future?
Yeah, it's in fact, I didn't mention it, but we were asked, my group does that, they still do it, it's not my group anymore, look at orbital decay, and before we launched the last servicing mission, we looked at the orbit, and we said it was going to be good for at least 2023. I think it's going to be good even beyond that, because the solar activity didn't ramp up like we thought. So I think we got time. That was part of the reason, in fact, I didn't mention this either, but we chose not to raise the orbit on the last mission because we thought it would be okay for a decade, and because the way you play the numbers game, in order to be able to launch, you've got to be able to prove that you're below a certain threshold of risk due to debris hits. And the way you manage that number, pre-flight anyway, is you say, well, I'll fly half the mission at a lower orbit. So we'll go do Hubble, and then we'll come down, and that'll make the numbers work out.
So the trade-off is, like, in a lower orbit, I would assume that debris would be less of a concern because it'd be more likely to burn up, but the higher up you go, the harder it is to service. And
Yeah, lower orbits are generally self-cleaning over time, so the concentration is usually better in the lower orbits. It used to be you could go up to like 800 kilometers and be better still, because there isn't much up there until the Chinese did their ASAT test in 2009, I think it was. So now debris is going to be raining through Hubble's orbit for the next 100 years.
Judy James Grant.
Can you comment on the major improvement of JWST over HST?
Well, a lot of people say that JW is a successor to HST, and I've always disputed that, because JW will be remarkable and it'll do some great things, but it won't do what HST does. It's an infrared telescope. It's much larger. It's 6.2 meters. What is the 6.5? 6.5. So it's designed to look at the very earliest stars, the very earliest galaxies that are highly redshifted. So it's going to do fabulous science. It just isn't the science that HST does. When HST is decommissioned, there won't be anything that can do what HST can do. So it's the successor in the sense that it's the next big space telescope, but it's not scientifically equivalent.
James?
How is James Webb going to be launched?
On an Ariane, as part of ESA's contribution, and it's going to go to L2, and a lot of, so it all gets folded up to go in the fairing of the Ariane. The mirror is segmented and it folds up, and the sun shield is segmented, so it folds up. And the idea is it's going to get there, and all this stuff's going to deploy, and it all will be well. I certainly hope that's true. Before I left NASA, I advocated putting what we call a grapple fixture, which is the thing that's on HST that allows the robotic arm to grab it. Put one of those on James Webb, so that if for some reason it doesn't deploy, you might at least be able to send something out that could grab it and shake it and maybe get it to work. When I left, I couldn't get anybody interested in that idea, actually. Although I was talking to Dave LaCrone the other day, who said he thought there was a grapple fixture on James Webb. So I'm actually not sure whether they did that or not. I had heard they hadn't, but I don't know. Do you know, Greg?
No, I was just thinking about it. Sure.
I worry a little bit about whether all that's going to work. And I didn't think they'd land Curiosity on Mars either. I thought that had no chance. So my track record's not very good at estimating the likelihood of success of these things.
Steve, what has all that debris done to the main mirror?
As far as we can tell, I mean, it must have been hit, but as far as we can tell, there's no performance effect that we can measure. In fact, I don't know to what extent it contributes to the time-dependent loss of power from the solar arrays, but otherwise there's nothing that I've ever seen from HST that you could say, well, maybe that hinge pin, but nothing that you could point to a debris hit that said, hey, it has compromised some aspect of the telescope.
I think the biggest degradation comes from cosmic ray hits in the detectors. So the detectors degrade over time, charge transfer problems.
I might add, though, for the James Webb, the loss of the ultraviolet capability is it's not a good thing,
No.
particularly for planetary.
They want to build a 10-meter optical telescope in the next 20 years.
Okay, Steve, thank you so
Thank
much.
you all for coming.